Our project is an Angry Birds-inspired automated targeting system built in LabVIEW using NIDAC. The VI is organized as a state machine with idle, load, aim, fire results, and reset. The webcam is a digital vision sensor that detects the green pig using HSV thresholding, then calculates centroid Y and converts it to height in meters using calibration. The VI starts in idle state where it waits for the user's input and also retracts the solenoid. And once the Boolean is clicked, it would also move on to the next state, which is the load state.
So the purpose of this state is to identify which projectile is loaded before the system moves on to the aiming and firing stage. For that, we use a color sensor, which is a digital frequency output sensor that contains the filtered photodiodes for red, green, blue, and clear, and that outputs a square wave frequency whose value depends on the reflected light intensity. In the VI, this section is placed in a flat sequence structure so that the steps happen in order. First, the sensor channel is selected, then the waveform is read through the NI-DAC, and then the measured frequency is scaled into a percentage through the VI. In the VI, we use a 12K Hertz value, which is the full scale maximum at the slowest sensor setting, and this is used in order to reduce the aliasing risk and make the signal easier for the DAC to read. Once the dominant color is identified, the system knows which projectile is loaded and can move on to the aim stage.
So the ultrasonic sensor's duty is to provide distance on how far the pigs are from the actual ramp itself. This can be done through the VI because the ultrasonic will be sending signals such as trigger and echo, as the VI will pick up on this and be able to determine the distance. This can then be used in order to provide calculations on the angle we'll be needing to set it to, as it will be done through a math block which will include many other variables. So then this will help tell us the angle we need to set it to. And then to set the angle itself, we will be using the servo motor. The servo motor is going to be an actuator, and it's going to be operated on a pulse width modulated controller. So the way it works is that it's going to be sending pulse widths over to the actual servo in order to change the angle. So how it works is that if we give it a certain angle, there will be calculations done on it in a flat sequence, and they will be done in a correct order specifically. So what will happen is once these calculations are done, it will send a signal through the NI-DAC all the way to the servo.
In the fire state, the solenoid is activated as a digital on and off actuator to launch the projectile. This state connects the calculated launch decision to the physical system by delivering a short firing impulse before the VI moves to the result stage.
In the results stage, we use a force-sensitive resistor to detect whether the pig is on or off the platform. The FSR is an analog sensor whose resistance changes with applied force, and in our setup, it's part of a voltage driver that converts resistance change into a voltage that our DAC reads. Although the DAC has a range from 0 to 5 volts, we only use 0 to 1 volt threshold for detection. The voltage is between 0 and 1 volts, and the system considers the pig to be on the platform, but if it rises above 1 volt, the pig is considered off. This works because when the force is applied, the FSR sensor decreases its resistance, which keeps the measured voltage lower. When the pig is removed, the resistance increases, and the voltage rises. So in our VI, the FSR is used as a simple threshold detector, and nothing more.
And lastly, in the reset stage, the state machine is able to go back to the idle stage and start the whole process over again without having to stop the code.